The world turns under a quilt of clouds. Children walk to school. Ships trace white scars across the ocean. The air hums with the electricity of human life. Traffic lights flicker, factories breathe, and voices weave together into the great unbroken song of civilization. Above it all, in the deep black silence beyond the sky, a solitary traveler drifts. It is a fragment of ancient stone, older than any mountain, older than the seas, older than life itself. It was born in the furnace chaos of the solar system's birth, shaped by collisions and gravity, carried for billions of years along a path no human eye could see. It has no will, no malice, no thought, only the momentum of its creation. In the year 2032, that path may cross our own. On that day, if the numbers are right, the sky will open with fire. A streak brighter than the sun will descend, the air before it crushed into a wall of heat and wind. The ground will shudder. The seas may rise in walls hundreds of feet tall. Dust will bloom into the stratosphere, veiling the sun, cooling the earth. The rhythm of human days will break. NASA's instruments whisper a possibility, small but real, that an asteroid known as 2013 Television 135 could bring such an ending. It is not fiction. It is the mathematics of orbits, the inevitability of physics. Our species has lived through countless dawns believing the future was promised. But the universe offers no promises. Only trajectories, only collisions, only the quiet ancient stones that drift in the dark, waiting for the day their story intersects with ours. And now, one of them has a date. It began, as many discoveries do, not with a grand revelation, but with a faint, almost invisible flicker against the backdrop of eternity. The year was 2013. In the still hours of night, an automated sky survey scanned the heavens. The telescope's camera moved in slow arcs, capturing countless stars, galaxies, and dark stretches of nothingness. Among them was a single point of light, barely brighter than a ghost's breath, shifting slightly from frame to frame. To the untrained eye, it could have been a glitch in the software, a wandering satellite, or the brief flash of cosmic rays striking the sensor. But astronomers at the Crimean Astrophysical Observatory in Ukraine recognized the pattern. The movement was deliberate, steady, bound by the laws of celestial mechanics. This was no stray reflection, it was a body in motion, orbiting the Sunday. In their logs, it received a temporary designation, 2013 Television 135. It was not yet famous, nor feared. At that moment, it was simply another of the countless near-Earth objects cataloged each year, pieces of cosmic debris from the dawn of the solar system, wandering in the gravitational web spun by the sun and planets. But even the smallest discoveries demand curiosity. Over the following nights, telescopes from other observatories in Spain, Italy, the United Kingdom turned toward the coordinates. Each image captured the same point of light, now moving predictably against the fixed stars. Data flowed into computers, where mathematicians began the work of orbit determination. This is the quiet heart of planetary defense, the patient plotting of an object's path through the solar system. Each observation is a pinprick of certainty on a vast, curved map of space and time. Connect enough of those points, and the future can be foretold. When the first calculations emerged, the result was routine. 2013. Television 135 belonged to the Apollo group of asteroids, space rocks, whose orbits cross that of Earth. Apollo asteroids are not rare. Thousands are known. Most pass harmlessly by, coming no closer than the Moon's distance. The early trajectory suggested this too would be a near miss. But probability is a living thing in astronomy. It shifts and evolves as more data arrives. Weeks later, after refining the measurements, the team noticed something unsettling. On a certain date, in 2032, the Earth and 2013 television 135 would pass within the same region of space, a region small enough that the possibility of collision could not be dismissed. The numbers spoke in the cold, precise language of mathematics. A 1 in 6,3000 chance. To the general public, this sounded reassuringly remote. To planetary scientists, it was a signal flare in the dark. For an object hundreds of meters across, even such a slim probability carried profound implications. NASA's Near-Earth Object Program soon confirmed the findings. They entered the asteroid into the Century Risk Table, a list of celestial bodies with a measurable chance of hitting Earth. The name 2013 Television 135 joined the catalog of cosmic threats. In the control rooms and observatories, the mood was not one of panic, but of concentrated attention. The memory of past impacts lay heavy on the minds of scientists. 66 million years ago, an asteroid roughly 10 kilometers wide struck the Yucatan Peninsula, ending the reign of the dinosaurs and reshaping Earth's biosphere. The Chicxulub impact was an extinction event, a reminder that space does not negotiate. In 1908, a smaller object, perhaps 50 meters across, exploded over the Tunguska region of Siberia. The blast flattened 2,000 square kilometers of forest. If it had struck a city instead, millions could have died. And in 2013, the same year, 2013, Television 135 was discovered. The Chelyabinsk meteor, a rock only 20 meters wide, entered Earth's atmosphere over Russia, shattering windows and injuring over 1,000 people. Its shockwaves circled the globe twice. The scale varies, but the pattern is clear. Earth is not immune. It never has been. From that moment, the story of 2013 Television 135 was no longer confined to observatory reports. It moved into scientific conferences, into the plans of space agencies, and into the archives of planetary defense strategy. The Crimean astronomers who first spotted it became quiet custodians of a question larger than themselves. What happens if the probability grows? Other telescopes were called upon to join the watch. The Catalina Sky Survey in Arizona, Pan-STARRS in Hawaii, and facilities across Europe began periodic tracking. Each pass of the asteroid, each time it reflected sunlight back to our lenses, would sharpen our picture of its orbit. But the challenge was immense. Asteroids like 2013 Television 135 are not easy targets. They vanish into the sun's glare for months at a time, invisible to Earth-bound eyes. When they return to the night sky, they may appear only as faint, flickering points. To find them, astronomers rely on time and patience. Years would pass before enough data could be gathered to definitively rule out a collision or confirm it. Meanwhile, in the media, the headlines flared. Asteroid could hit Earth in 2032. Some outlets spoke with measured accuracy, others with sensational urgency. But inside the planetary defense community, the truth was less dramatic and more sobering. This was a rehearsal, a warning that did not require certainty to matter. Because whether or not 2013 Television 135 strikes Earth, it represents a class of threats that will never go away. The solar system is littered with such bodies, leftover fragments from the birth of planets, shaped by billions of years of collisions. They move along invisible highways of gravity, occasionally crossing our orbit. And each crossing is a roll of the cosmic dice. The Crimean discovery was, in many ways, a stroke of fortune. An asteroid cannot be deflected or destroyed if it is not first seen. The earlier the warning, the better the chance of acting. And here at least, the warning was almost 2 decades long. But a date had been marked on the cosmic calendar, the 26th of October, 2032. A day when, according to the best measurements available, a rock the size of a city block could meet our world. For now, the probability was small. For now, the asteroid was only a distant speck, moving silently among the planets. But probability is not a promise. And the history of Earth is written with the craters left behind when probabilities became reality. It is not the certainty that unsettles scientists. It is the possibility. For in that slim, statistical shadow, a 1 in tens of thousands chance lives an outcome so vast in consequence that numbers alone cannot contain it. Asteroid 2013. Television 135 is not an enormous world killer in the style of the Chicxulub impactor. It is smaller, yes, but still unimaginably large in human terms. Its estimated diameter, 400 meters, is enough to hold the length of multiple football fields laid end to end. Its mass is measured in hundreds of millions of tons. And mass, in space, is potential energy waiting to be unleashed. If it were to strike the Earth, that energy would be released in an instant, a detonation so immense it would dwarf every nuclear explosion in history combined. Calculations suggest an impact yield exceeding 2,500 megatons of TNT. That is more than 50,000 times the power of the Hiroshima bomb. But raw numbers are abstractions. To imagine the reality, one must translate them into the language of landscapes and lives. At the moment of impact, a blinding fireball would form, brighter than the sun, visible across continents. The heat would sear the ground for hundreds of kilometers, igniting forests, fields, and cities in seconds. A shock wave, moving faster than sound, would flatten everything in its path. Skyscrapers would collapse like sandcastles under an invisible tide. The pressure would rupture eardrums, shatter windows, and fling debris with the force of artillery shells. If the asteroid struck land, a crater several kilometers wide and hundreds of meters deep would scar the Earth's surface. Beneath that crater, bedrock would liquefy, vaporized in the furnace of impact. If it struck the ocean, the result would be no less catastrophic. Walls of water, tsunamis, hundreds of meters high, would race outward, crossing entire oceans in hours, sweeping over coastlines without warning. But the most dangerous effects would not be confined to the immediate blast zone. Billions of tons of pulverized rock and dust would rise into the atmosphere, forming a shroud around the planet. Sunlight would dim. Global temperatures could drop. Crops would fail under shortened growing seasons. Hunger would spread. It would be, in essence, a man-made winter, except it would not be man-made at all. It would be the sky's own revenge, born from a rock that had drifted silently through space for billions of years. And here lies the deeper shock. Such impacts are not rare on geological timescales. The Earth's crust is littered with scars, craters carved in an instant, then softened by wind and rain over millions of years. Some are small, remnants of local devastation. Others are vast enough to have rewritten the entire story of life. The Chicxulub crater in Mexico is the most famous, a reminder that an asteroid just 10 kilometers wide ended the age of dinosaurs, not through fire alone, but through the chain reaction that followed. The impact sent vaporized rock into the sky, blocking sunlight for years, collapsing ecosystems in a cascade of extinctions. 2013. Television 135 is far smaller than Chicxulub's killer, yet its impact would still be a turning point in human history. It could erase nations. It could destabilize the climate for decades. It could send civilization into a spiral from which it might never fully recover. The unsettling truth is that the last century has been unusually quiet by cosmic standards. The largest confirmed asteroid strike in human history. The Tunguska event of 1908 occurred in an uninhabited part of Siberia. Had it struck over a city, the casualties would have been unthinkable. Scientists understand this quiet not as a sign of safety, but as a statistical lull, a pause in a long rhythm of impacts stretching back to Earth's birth. Sooner or later, the cycle will resume. And that is why 2013 Television 135 is not merely another rock cataloged by observatories. It is a reminder that probability is not protection. The mathematics of orbital mechanics offer no comfort. In space, the line between harmless passage and devastating collision can be thinner than a thread. A tiny nudge, a gravitational whisper from Jupiter, or the faint push of sunlight warming one side of the rock more than the other, could shift its path just enough to bring it into our future. That nudge could have already happened. Or it could happen years from now. Or it might never happen at all. The universe offers no guarantees. And so the shock is not just in what might occur on a single day in October 2032. It is in the realization that this has always been true. For all of human history, civilizations have risen and fallen under a sky that could at any moment deliver a rock large enough to undo centuries of progress. Until the invention of telescopes, such threats were invisible, arriving without warning. Now, we can see them coming. And sometimes, seeing is worse. It is one thing to live under threat unknowingly. It is another to count the years until a possible collision, to watch the object grow incrementally brighter in telescopes, to refine its path with each observation, knowing that each new data point could either lower the risk or confirm the worst. In laboratories and conference rooms, scientists talk about impact probability, as if it were a sterile concept. But behind the numbers is a reality that is not sterile at all. A 400-meter asteroid is not an abstract idea. It is a mountain of stone moving at tens of kilometers per second. It is kinetic energy incarnate. It is, in essence, a weapon forged by no hand, aimed by no intention, but capable of reshaping the biosphere. And it is not alone. 2013. Television 135 is simply the one we have marked with a date. Thousands of other near-Earth objects drift through similar orbits. Some we have found, many we have not. The gap between what we know and what is out there is vast, and in that gap lies both danger and urgency. This is the quiet terror of planetary defense. It is not about panicking the public. It is about acknowledging the truth. The universe does not need to be hostile to be dangerous. A stray rock, indifferent and ancient, is all it takes. In that sense, the asteroid is not just a threat to life. It is a mirror held up to civilization itself, asking whether we are capable of acting on a danger we can see decades in advance. Whether we can move beyond politics and borders to face something that belongs to no nation and threatens them all. The possibility of a 2032 impact is slim, but the shock is in knowing that slim is enough. That, given enough time, an asteroid like this will hit the Earth. The only question is when. And somewhere, beyond the edge of sight, 2013, Television 135 continues on its path, guided by the same forces that have shaped the planets and moons, silent, steady, unconcerned with what it carries in its wake. The investigation began with a point of light and widened into an anatomy of a threat. Each new observation was a stitch in a tapestry that could, if read correctly, tell the future. The task was not to imagine catastrophe, but to measure it quietly, precisely, without panic, without comfort. Whenever Earth's orbit and the asteroid's vantage allowed, telescopes gathered photons the way a shoreline gathers foam. On some nights, the rock brightened just enough to let cameras push the exposure deeper. On others, it slipped into solar glare and became a rumor hiding in daylight. Patience was the first instrument. Time, the second. From observatories in Hawaii and Arizona, from La Palma and La Silla, the routine was the same. Track, subtract the fixed stars, measure the motion. Each timestamp anchored the object to the celestial sphere, letting orbital fitters refine elements that were once loose and now drew tight. Every coordinate narrowed the corridor through which the asteroid would travel years hence. In computer rooms lit by the soft glow of terminal windows, curving lines of code drew millions of trial orbits, nudging them with the known gravities of planets, moons, and the faint tug of sunlight itself. Sunlight is not neutral. It warms one hemisphere of a tumbling stone more than the other. Heat radiates away, and with it, momentum and almost unimaginable gentleness known as the Yarkovsky effect. Over years, this thermal breath can push an asteroid across lanes of space like a slow current on a dark river. If a future keyhole, a tiny gravitational doorway near Earth, lay along its path, Yarkovsky could be the difference between a near miss and a later return that is not a miss at all. The models learned to speak that language, adding a line to the equations where radiation became a force. While the orbit sharpened, astronomers turned to the nature of the thing itself. Composition is destiny in planetary defense. A metallic monolith holds together under stress. A loose rubble pile absorbs impact like sand. Through visible and near-infrared spectra, analysts searched for the fingerprints of minerals. The broad, shallow absorption bands of carbonaceous chondrite. The brighter, more reflective signature of silicate-rich S-types. The stark gleam that hints at nickel iron. When the asteroid rose high enough and the weather complied, polarimetry added another clue. Its subtle angle-dependent dimmings translating into albedo how much light the surface returned. Combine albedo with brightness, and diameter falls out of the math like a whispered confession. Thermal infrared, when available, was more direct. Under a sky cold enough to let mid-IR detectors drink starlight without boiling and noise, astronomers measured the heat the rock shed at night, its glow just beyond the reach of human sight. From that glow came a sense of size that brightness alone could not fake. A dark object and a small bright one can shine the same, but their warmth betrays their truth. Rotation, too, became a character in the story. Light curves, minute-to-minute changes in brightness as the asteroid spun traced a sine wave across nights of data. Regular, single-period modulations suggested a coherent body. Erratic, double-peaked signatures hinted at elongation. Strange, aperiodic wobbles whispered of tumbling. The spin rate put limits on cohesion. Rubble piles, bound more by gravity than by strength, cannot spin much faster than a few hours without flying apart. A fast spinner might be a single stone, dense and stubborn. A slow one, perhaps a cluster of boulders, about a common center. Between them lay a spectrum of possibilities, each with a different response to a human push. The possibility of a companion was not dismissed. Many near-Earth asteroids are binaries, a larger primary shepherding a small moon. Stellar occultations, moments when the asteroid's shadow slips across Earth and briefly extinguishes a star, offered a chance to sketch its shape in silhouette and to catch, if fortune was kind, a second, smaller shadow trotting beside the first. Coordinated teams spread across predicted ground tracks with portable telescopes, their clocks synchronized to atomic time. In those few seconds of darkness, geometry became revelation. A dip here, a dip there, separated by a heartbeat, the subtle code of companionship. Radar, when the geometry allowed, promised more. In an era before silence fell over Arecibo, its great dish, and now, chiefly, goldstones could paint the asteroid with radio waves and receive the echo, transforming time delay and Doppler shift into pixels of distance and speed. In those grainy luminous frames, stones become worlds, facets and ridges, lobes and necks, a contact binary perhaps, two once separate bodies fused by a slow kiss. Radar returned rotation unambiguously, sketched size without guessing albedo, and sometimes revealed boulders resting on slopes in a field of microgravity. For planetary defense, it was the sharpest eye we possessed. When distance or power or the sky's alignment denied that eye, its absence was felt like a missing sense. All the while, the orbit solution iterated. Sentry and Enio dyes, guardians of risk, recalculated the Palermo and Torino scales with each new arc of data. Small numbers moved like tides around zero, a decimal point more dangerous, a decimal point less. The public looked for certainty in those shifts. The scientists looked for convergence. There is a moment in orbital refinement when the future stops flickering and begins to cohere. Until then, the prudent mind holds both outcomes in balance, a pass that teaches and a strike that tests. Beyond trajectories and taxonomies lay the practice runs for consequence. Numerical hydrocodes, ISAIL, spheral, Connecticut H, and their kin took an impactor of a given size, speed, angle, and composition and drove it into digital Earth. The ground liquefied in equations, shock fronts bloomed in false color, vapor plumes rose with the physics of EOS tables that had been tested in laboratories with metals and lasers and diamond anvils. For land strikes, the models traced thermal radiation across terrain maps, drew blast overpressure rings, calculated seismic wave attenuation through crustal layers, and mapped ejection blankets that would fall as ash-gray snow across provinces. For ocean entries, they flung columns of water upward into temporary mountains and let gravity tug them back into rings of traveling catastrophe, their run-up heights modulated by continental shelves, bays, and headlands. Climate modelers, those who parse the sky's moods, fed the outputs into atmosphere-ocean general circulation models. How much soot would loft to the stratosphere from ignited forests? How much dust and sulfate aerosol would linger after rock met rock at orbital speeds? How far would sunlight wane? For how many seasons would crops lose yield? The models coughed up maps of cold summers, altered rainfall, and winds that would carry particulate veils around the world like a slow-moving tide. Each assumption angle of entry, composition, target, branched into forests of futures. In those forests, policymakers would one day need a path. But before policy came precision, keyholes, tiny target windows in space, sometimes only hundreds of meters across, haunted the close approach simulations. If the asteroid threaded one during a pass years before 2032, Earth's gravity could bend its orbit just enough to schedule a future impact. The computation of keyholes is the geometry of destiny. Where must we not be? When must we not let it pass? And if a deflection were needed, by how much and by when? A delta V of millimeters per second, applied years in advance, can move a mountain across a planet's radius. Applied late, it moves nothing at all. Internal structure remained the question that refused easy answers. Seismic probes require landers. Core samples, a rendezvous. Both are feats measured in budgets and years. So inference stood in. Bulk density estimates emerged from size and brightness, porosity from comparison with meteorite analogs, cohesion from spin thresholds. All were imperfect, yet all were better than the dark. A body of gravel holds together differently from steel. A push that saves the world with one would shatter the other into a swarm many bullets instead of one. The literature held case studies, warnings and footnotes. Shoemaker Levy 9, tidally shredded before striking Jupiter. Didymos and Dimorphos, their encounter with a human impactor yielding a plume of ejecta beyond expectations. Nature's response is generous with surprises. Around the core work gathered the human scaffolding. International observing campaigns coordinated windows when the asteroid rose. Time allocation committees weighed the urgency against other sky demands. Software pipelines were tuned to catch faint motion against crowded star fields. Ephemerides were published with uncertainties flagged like weather fronts. Each small improvement, an extra tenth of a magnitude in sensitivity, a better background subtraction, a cleaner streak removal, tugged the orbital corridor a little narrower. Through it all, the tone stayed measured. In papers and telecons, phrases were chosen carefully. Non-zero impact probability. Further observations required. Post-fit residuals improved. Yarkovsky unconstrained. The science demanded restraint. The stakes demanded clarity. Between them, a kind of calm emerged. The calm of professionals tracing outcomes in a domain where drama is a distraction. Outside, the night remained what it had always been. The asteroid's motion across it was patient, almost tender, a bead on an invisible wire. It did not argue, and it did not reassure. The numbers did that, and sometimes they did neither. There is a point in any investigation where the object becomes less of an intruder and more of a teacher. 2013 television, 135, stone, vacuum, sunlight, taught the discipline of uncertainty. It taught the physics of small forces over long times, the art of seeing with instruments that never touch, and the humility of planning for events that may never arrive. It drew from us a portrait of ourselves, a species that can turn photons into futures and futures into plans. And still, there were nights when clouds covered the domes and the equations waited on desks, and the rock moved on without witness. Those nights belonged to the solar system alone. Those nights said, "Remember that the clock you measure is not the only clock that ticks." In that truth, the deeper investigation did not end. It only thinned into the silence between oppositions, waiting for the sky to open again, for the next bright point to climb the CCD, and for the pencil to cross another day off the calendar that led toward a year written in our minds like a vow. The numbers on the orbital charts shift like the shadows of clouds. Small changes, subtle, but in the language of celestial mechanics, each one is a new possibility. The path of 2013, television 135, is no longer a mere line on a graph. It is a thread stretched tight across years, with one end tied to the cold silence of the asteroid belt and the other to the living skin of Earth. And it is pulling tighter. Planetary defense scientists speak in careful tones. The probability of impact remains low, but the margin for action is vanishingly small. In theory, we have the technology to push it away. A kinetic impactor, a nuclear standoff burst, even the delicate tug of a gravity tractor. In practice, every method is a gamble. We have never deflected something of this size on a collision course, and in space, there are no second attempts. The clock is the true enemy. To move an asteroid's path by a safe margin, action must come years before the predicted impact. But to commit too early is to risk striking a harmless rock and scattering it into a deadly swarm. To act too late is to ensure nothing can be done at all. Between these extremes lies the narrow, treacherous ground where decisions must be made. Beyond the engineering, there is politics. If the predicted impact zone lies within one nation, will others demand intervention? Will the country in its path resist a foreign spacecraft's approach? Even the idea of using nuclear devices in space is wrapped in treaties and suspicion, and the asteroid does not wait for diplomatic signatures. There is another fear quieter, but harder to dismiss. If 2013 television 135 is a rubble pile rather than a single solid mass, a forceful deflection could shatter it into dozens of fragments, each with its own deadly trajectory. Instead of one impact site, there could be many. In simulation rooms, the impacts play out. An ocean strike sends walls of water tearing toward distant coasts. A land strike turns entire regions into fire and ash. The models are indifferent to borders or flags. They only follow physics, and physics does not negotiate. The mystery now is no longer about the asteroid's existence. It is about us, about whether a species that can leave its planet can also protect it, about whether we can act not as nations, but as a civilization. And above our divisions, somewhere in the black silence beyond the moon, 2013 television 135 continues to drift slow, cold, and perfectly on time. Some scientists look at 2013 television 135 and see only a rock, a drifting relic from the birth of the solar system, moving on a path shaped by chance. But others see it as something more. They see it as part of a cosmic story far older than humanity. One idea, quietly discussed in planetary science circles, is that asteroids like this are not just harbingers of destruction. They may also be the seeds of life. 4 billion years ago, countless rocks from space struck the young Earth. In their interiors, shielded from radiation, lay complex organic molecules, amino acids, nucleobases, the raw ingredients of biology. Delivered in fire and impact, these building blocks may have been the first spark of the chain that led, eventually, to us. In this view, the same class of objects that could end our story in 2032 may have helped begin it in the deep past. Others focus on the mechanics of its journey. In the vast asteroid belt between Mars and Jupiter, billions of fragments orbit in uneasy balance. Over millions of years, gravitational whispers from the giant planets and subtle pushes from sunlight, the Yarkovsky effect, can tip these bodies onto new paths. A single near miss with another rock can shift a trajectory just enough to send it inward toward Earth. This process is random, yet inevitable. It is not just Earth's fate. Any inhabited world would face the same lottery. Some theorists expand the question even further. They imagine civilizations scattered across the galaxy, each confronting their own 2032 moment, a point when the survival of their species depends on whether they can act in time. In this way, asteroid defense becomes a test of maturity for intelligent life. Those who pass endure. Those who fail vanish into geological memory. There are darker speculations that perhaps in the grand cycles of the cosmos, destruction is not a flaw but a pattern, that extinctions clear the way for new forms, new stories, new worlds. The asteroid, in this telling, is not an intruder but a player in an ancient rhythm, the same rhythm that ended the reign of the dinosaurs and allowed mammals to rise. And then there are the long-term thinkers who look beyond 2032. If 2013 television 135 misses, and it may, will we learn the lesson? Or will the next rock catch us unprepared?
The solar system is full of them, silent and cold, each on its own clock. In 1,000 years, in 10,000, another will come. This is not the last warning we will receive.
Somewhere in all of this speculation lies a strange symmetry. That we live at the moment in history when our species has both the awareness of the threat and the means, at least in theory, to stop it. Whether we choose to act and how may be the measure by which the future remembers us. Above the Earth, the asteroid continues on its path, neither cruel nor kind. To it, we are not a target, we are just in the way. In the darkness above the atmosphere, silent sentinels sweep the sky. Some are ground-based, like the twin domes of Pan-stars in Hawaii, scanning the night for the faintest, slowest moving points of light. Others drift in orbit, their optics untouched by clouds, peering into the glare of the sun where earthbound eyes cannot look. All of them have one mission: to know, as early as possible, when the next rock is coming. 2013. Television 135 is among those under constant watch. Every few months, its position is measured again, the arc of its path refined. The Vera C. Rubin Observatory in Chile, soon to awaken, will turn its 8.4-meter mirror toward the stars, capturing the entire visible sky every few nights. Its cameras will see motion where human eyes see stillness, and in that motion, the difference between safety and impact may be found. Far from Earth, the European Space Agency's Gaia spacecraft maps the positions of more than 1 billion stars with exquisite precision. Even the tug of those distant suns plays into the slow dance of an asteroid's orbit. Closer to home, radar dishes like the Goldstone Deep Space Communications Complex send pulses of radio energy out to 2013. Television 135, timing their echoes to build a picture of its shape, its spin, its roughness. On the ground, supercomputers work without pause. They take in the data orbital vectors, thermal radiation, gravitational influences, and run millions of simulations. Each is a roll of the cosmic dice, a possible future. Some show the asteroid passing harmlessly by, others end in fire. And there are the experiments in planetary defense itself. In 2022, NASA's DART spacecraft struck the small asteroid Dimorphos, shifting its orbit. The world watched as a concept leapt from theory into proof. ESA's Hera mission will soon follow, studying the aftermath in detail, learning how rock and rubble react to a kinetic blow. If deflection is ever needed for 2013 Television 135, these lessons will be our foundation. In meeting rooms with no windows, policymakers and scientists run what they call tabletop exercises. They simulate the 2032 scenario, the uncertainty of an impact point, the politics of evacuation, the coordination of nations. How do you move millions in days? How do you prepare for seas that will rise in hours? The drills end, but the questions linger. Through it all, the asteroid moves in silence, unaware of the telescopes that track it, the algorithms that predict it, the engineers who design ways to alter its fate. Every observation adds a brushstroke to the portrait of 2013, Television 135. Yet the final image, the one that shows whether it strikes or passes, will not be clear until the last data point is written. Between now and 2032, the tools will sharpen, the simulations will grow more precise, and the network of watchful eyes will widen. But in the end, the rock's path and our response will meet at a single moment in time. And in that moment, all the technology, all the planning, will either be enough or it will not. Night falls across the continents, and the cities glow like scattered embers beneath a vast, indifferent sky. Somewhere beyond that sky, the asteroid drifts silent, slow, older than the mountains, older than the seas. It carries no malice, no intent, only the inevitability of its orbit. The Earth has been struck before. Long before humans, long before cities, long before thought itself, impacts came like punctuation marks in the story of life. Sudden, violent, and final. Each one rewrote the script, ending chapters that had taken millions of years to write, and beginning others in the ash and quiet that followed. Now, for the first time, a species watches the next sentence being written in real time. We know the shape of the rock. We know its speed. We have a date circled on the calendar. And yet, the question remains, will we act? Or will we allow the story to unfold as it always has, with no hand to alter it? In some distant future, perhaps there will be others who stand where we stand now, watching their own sky for their own rock, wondering if they will survive. Perhaps every civilization that rises from dust must face this same trial. The test of whether it can unite not in war, not in conquest, but in preservation. If 2013 Television 135 passes us by, we will breathe easier. But the reprieve will not erase the truth it carries that the cosmos is not a safe harbor, that survival is never guaranteed, and that vigilance is the price of existence. And if it comes, there will be no time for politics, no time for division, no time for anything but the raw fact that we are small and the universe is vast. In the deep silence beyond the air, the asteroid continues on its path. It does not see us. It does not hear us. But if we choose, we can see it. We can hear the warning it carries. And we can decide in the narrow space between now and 2032 whether we will write the next chapter or whether the asteroid will write it for us.